All right, so what I'm going to do is we started lecturing on this chapter. I'm going to quickly review the stuff we went over last time, which was Monday. Finish this lecture and then do problems for chapter 11. So however far we get is what we're doing today. And next Monday we'll do chapter 12, and we'll be ready for the exam Wednesday, the following Monday. Okay? All right. So you saw we started talking about magnetic fields. In the next chapter, we'll learn that moving charges produce magnetic fields. But for now, so you had a magnet, and a magnet produced this magnetic field all around it. Okay. These are field lines, and field lines start at the North Pole and they end in the South Pole. Okay. And we saw that, well, okay, so here's this magnet and it creates a magnetic field all around it, all the way to infinity. The further out you are, the weaker the field gets. But then the question was, how do you know if there's a magnetic field? How do you detect a magnetic field? By moving charges. Very good. So you want to detect a magnetic field, what you need is a moving charge. You need a charged particle. It needs to be moving. Okay, so a moving charged particle in the presence of a magnetic field will feel a force. Okay, if the particle is uncharged, there won't be any force, and you don't feel the magnetic field. If it's not moving, you don't feel the magnetic field. Okay. And you saw that the magnetic force on a moving charged particle is perpendicular to the plane containing V and B. And you saw that this force is zero if V is parallel to B or anti-parallel to B. Okay, so that's the only time it won't exert a force on it. All right. Again, we have the right-hand rule. You use your right hand, and V cross B is that vector. Okay, and that's the direction of the force. All right. Again, if a positive charge is moving in this direction, there's the magnetic field. That's the direction of the force. And if a negative charge was moving in the same direction, what would be the direction of the force? I'm sorry? In the opposite direction. And you can see that from the equation. Force is QV cross B. Okay. So you figure out the direction of this vector. You figure out the direction of this vector, which is that. And if Q is negative, the force is in the opposite direction. Okay? All right, we saw all of that. And here are some magnetic fields. I think some of the stronger fields can get up to 100 Tesla. In MRI units, you can have fields up to 3 Tesla. On the surface of the Earth, it's 1/10,000th of a Tesla. Okay? And so we defined a new unit called a Gauss for that, to measure planetary fields. Okay, we saw all of that. This indicates a magnetic field coming out of the plane of the paper. This indicates a magnetic field perpendicular to the plane going into the plane of the paper. Okay. And then we saw if you have a current carrying conductor, if there's a current flowing in a conductor, well, a current constitutes a bunch of charges moving. Here the force on each charge, and that's the number of charges moving in the presence of the field. And so there is a force on a conductor, on a current carrying conductor. And the force is I L cross B. The vector L is the length of the conductor in the magnetic field, and the direction of the vector of the length L is the direction of the current. So in this diagram, L is in that direction. In this diagram, L is in this direction. Okay? So for this guy, there is L. For this guy, there is L. Okay. Anyway, so here's the force on a current carrying conductor of length L. Okay. So, and then we saw that, so if the conductor is not a straight conductor, but it's a curved conductor, you just break up the conductor into little pieces, find the force on each little piece, and then sum up all the forces. So for instance, if this was in the plane of the sheet and this was in a uniform field, the force on this guy would be, using the right-hand rule, ds cross b. ds cross b, the force would be coming out of the plane, okay? And the force on every little piece is coming out of the plane. And you could get the total force. You saw that in a uniform magnetic field, the total force on a closed loop is 0. The total force is 0, but the torque is not. So for instance, here is a uniform field. You have a loop, closed loop carrying a current. The force on this guy is 0, on this guy is 0, on this guy the force is in that direction. And on this guy, there's an equal and opposite force in this direction. So the net force is 0, but these two forces have a torque on this thing, and they'll rotate this. They will rotate this loop of wire. And they'll rotate the loop of wire about this axis like that. All right. So you see what is happening. If you use your right hand, point your fingers in the direction of the current. Your thumb points in the direction, so we assign an area vector in the direction of your thumb. And what is the torque trying to do? It's trying to line up the area vector along with to the magnetic field. That's what it's doing, okay? So you point your fingers along the direction of the along the direction of the current, and this area vector is being turned towards the magnetic field. That's what the torque is trying to do, okay? All right, and so use that idea in electric motors, okay? So we'll show this. Here's another example. So here's a loop of wire carrying a current like that. Your thumb is pointing in that direction with your right hand. And the forces on these two guys, are canceling each other. These forces are making the loop turn, and you see the loop is turning such that the area vector is being lined up with the magnetic field vector. Okay? A current carrying loop of conductor, we give it a special name because it's very useful. What is it called? That's called an electromagnet, because this produces a magnetic field very similar to a bar magnet. Okay? So a current carrying loop is like a magnet. Okay, so its magnetic field. So here is the magnetic field of a bar magnet. Okay. And the magnetic field of a current carrying loop is very similar. Okay. So this fellow is called an electromagnet. Okay. Now, the advantage of this guy is, see, if you get tired of this magnetic field, you can't turn this guy off. This guy you can turn him off. You can change his strength. You can reverse the direction of the current and reverse the magnetic field. Okay, so this guy is very versatile. Okay, the strength of this magnet. So mu, this is called the magnetic moment, and it points from the south pole to the north pole, if you want to roughly think of it that way. The strength of this magnet or the magnetic moment is N is the number of loops of wire you have, I is the current, and A is the area of the loop. Yep. And again, the direction of the area vector is figured out using the right-hand rule. Your fingers are pointing in the direction of the current, and your thumb is pointing in the direction of the area vector, or the direction of the magnetic moment. All right, you saw that you place a magnet or a loop of wire, current-carrying loop in a magnetic field, and it feels a torque, and the torque is mu cross B. Yep. And what is the magnetic field trying to do? What will the torque do? It will
turn towards the area vector?
There you go. Turn the moment towards the magnetic field. Okay, so here let's make sure we understand this. There is the magnetic moment, and if you have a magnetic field in this direction, okay, the torque is trying to line it up into the magnetic field. Okay, so that's what. And if the magnetic field was in this direction, there you would turn it in that direction. All right. All right, so that's what we studied. Okay, and the potential energy associated with the magnetic moment in the presence of a magnetic field is given by that expression. Remember, when the moment is being turned towards the magnetic field, potential energy is being converted to kinetic energy. Okay? All right, so that's where we had gotten last time, and you can use this kind of stuff to turn satellites. So imagine here's a satellite up there, up in space, 400, 500 miles away, and suddenly you want to turn it for some reason. Yeah.
So if potential energy is being converted to kinetic energy as it goes closer to the magnetic force.
To the magnetic field as it's.
Magnetic field, yes. So does it mean when the mu is parallel to the magnetic force is when the potential energy is the greatest?
Is the least.
The least.
Yeah. When it's opposite, it's the greatest.
Opposite is the greatest.
Yes, that's why the negative sign. When it's opposite, the dot product would be negative. Negative of negative would be positive. When it's parallel, that would be positive, and the negative sign gives it the least potential energy. Yep. All right. So this device is useful. Okay, let's say up in space you have the satellite. You're using this guy to bounce off TV signals or whatever for communication. And somehow it got bent like that. Now this become a $500 million piece of junk. Well, how do you get it straight back? Okay, so here's what you could do. You have this piece of wire, and there's the Earth's magnetic field. All you do is pass a current in this piece of wire. That'll turn toward the magnetic field. Okay, so initially the angular momentum of this thing is 0. As this wire turns this way, this will turn over. You got enough turn, you just turn off this current. Okay. So this is great. And if you turn it this way, the satellite will turn the other way. Okay? So these things are called torquers. Yeah. Now the deal with this thing is, so as you go further and further away, the Earth's magnetic field is getting weaker and weaker. So this thing is useful in low Earth orbits. Okay, you can't use this for geostationary satellites. You're too far away. Yeah.
So,
He had first.
so when it's in space and there's no, like, if it has the force to where it starts turning, does it keep going? Because there's
Soon as you stop this guy,
it stops turning?
yep, it's turned. Yeah. I showed you that bicycle wheel thing. It's the same idea.
Okay. Oh, okay.
Yeah. All right, your turn.
I answered my own question.
You don't need the teacher. All right, so these guys are useful. And again, why is this useful? Okay, back in the old days, the advantage of such devices is they use solar energy rather than thruster fuel. Okay, back in the old days, it used to be very expensive to get stuff up in space. Nowadays, Elon has made everything cheap, but so you didn't have to have thruster fuel. And also, I mean, how far do you plan to have fuel for? The sun is going to shine all the time, so once you have solar cells, they last 20, 30 years. All right, now let's make sure we understand this. Okay, what is this diagram showing you? It's showing you a magnetic field going into the sheet. Okay? So so for the recording, I'll say this. Now, if you throw a proton in this direction, V cross B, so if you turn the screw in this direction, V cross B is in this direction. The force on this proton will be in that direction. And this proton will turn like that. And when it's here, V cross B is in this direction. So you see the force is always towards this point. And so if you throw a proton perpendicular to a magnetic field, it goes around in circles. All right, so just a second. So here is a magnetic field. You throw a proton like that, and it's making circles. What did this guy do? The magnetic field trapped a charged particle. All right, why is this such a big deal?
Orbit?
I'm sorry?
Orbit?
Let's say you have protons that are at 3 billion degree Kelvin. If these guys were just moving around freely, they would instantly vaporize the walls. You don't want to hit that hot gas to hit the walls, that hot plasma to hit the walls. Well, just have a strong magnetic field. You got that trap. Fusion reactors. Okay, my friend, you have a question?
I was going to say, does it always form perfect circles? Or
Yeah, if it's perpendicular, and if it's not perpendicular, then it'll go in spirals, which is the next slide. Yeah, so if the velocity is perpendicular, it's a perfect circle, assuming the magnetic field is uniform.
does it also explain the Van Allen belts, or is that something else?
See, that's 2 slides ahead. All right, so we're getting there. So did you guys understand that? Very important. Magnetic fields can trap charged particles. They have to be moving. Okay. If they're at rest, then they're not moving. But then particles at rest, that's at 0 degrees Kelvin, and that doesn't happen. Okay. All right. So what this formula does is and that's the magnitude of the force on them. And that is the centripetal force that's making them go in a circle. That's equal to that. And so this is the angular frequency. Charge times the magnetic field divided by the mass. Okay? So lighter the particle, more circle it makes. Okay? So the proton and the electron have the same charge. And if you place them in the same field, okay, the electron will go around many more times than the proton. In fact, 2,000 times more than the protons, because the electron is 2,000 times lighter. Okay, so that's the angular frequency. All right, so if you throw the particle not perpendicular to the field but with an angle, this component of the velocity is unaffected by the magnetic field. Remember, components of velocities parallel to the field are not affected. Only the perpendicular component gives a circular orbit. So the net effect is a spiral, a helical path. Okay, so again here. All right, so let's make sure we understand this. So here's the magnetic field. If I throw a proton parallel to the field, what happens to the proton? There's no force on it, and it just will maintain its velocity. If I throw it perpendicular to the field, it'll go in a circle around it. If I throw it at an angle, it'll go on a helical path. But this guy is going in a helical path, he'll leak away if this magnetic field line is straight. All right, let's see how we fix that. Okay, so what is this indicating? This is a stronger magnetic field. This is a weaker magnetic field. This is a stronger magnetic field. This fellow here is called a magnetic bottle. Well, what's happening? At this point, the force is in this direction, which is making the proton go in a circle. These gray lines are paths of the proton. Okay, at this point, the force is in this direction. This is the centripetal force making go in a circle. This is the force that's slowing his progress in that direction. It's exerting a force backwards. What does a bottle do? What's the job of a bottle? What's your bottle doing? I'm sorry? What's your bottle doing? Yeah, holding stuff in. So here's the magnetic bottle. This is why it's called a magnetic bottle. This guy goes in that direction and feels a repulsive force and then starts back in that direction. These particles will go back and forth. Okay. Of course, if a particle has too much velocity, it'll escape, but in general, it'll hold a plasma. And here is one of nature's large magnetic bottles. Okay, so the field here is getting stronger. The field here is getting stronger. Okay. The star we are circling around is spitting out charged particles. And these guys get trapped in the Earth's magnetic field. Okay. And they have velocities in perpendicular component of velocity and parallel component of velocity, and these charged particles spiral back and forth, and the stronger fields will reflect them back. So the Van Allen belts are solar wind trapped in our magnetic field. Yeah. And they go between 1,000 kilometers to 45,000 kilometers. So the radius of the Earth is 6,000 kilometers. 45,000 kilometers is 7 times as far. Okay, so the Van Allen belt extend up to here on that scale, to the edge of this thing. Okay. So the Earth is surrounded by donut-shaped shells of these plasma. Okay. And the bottle is holding that plasma. Now, again, like the fast particles, some of them will leak, and if they come close to the Earth's atmosphere, within 50 miles, let's say 40, 50 miles, they start running into atmospheric atoms, and they'll excite them. And this is the result. Those excited molecules, when they de-excite, they will emit light. And those are the aurora borealis. In the northern hemisphere, they're called the aurora borealis. In the southern hemisphere, they're called aurora australis. Okay, so again, let's make sure we understand this. So I'm drawing a simple diagram. So here's a lithium atom. These particles hit the lithium atom. We don't have lithium atoms in our atmosphere. I'm just using this to illustrate. They excite this guy, and when this guy falls back, he emits a photon. And that's what this is. Okay.
Is that the reason why they're located where they are? Because the current going in the top and the bottom?
Right. So you have to come close to the Earth's atmosphere to knock them. Okay. And of course, when different transitions give you different colors of light, different molecules give you different colors of light. Yep.
So if we had, let's say, like a disaster
Mhm.
of a planetary kind and we lose our magnetic field,
Mm-hmm.
would we have aurora borealis or auroras all over the world? Or,
Yeah, but see, this is more concentrated, so this would be brighter. But if you had a constant stream, the light would be more diffuse, I would imagine. The stream of particles is not large enough.
Doesn't the aurora typically form after a solar flare occurs?
A solar flare is a more intense beam of solar wind, so you're getting more particles and it's more intense. So here's the beautiful thing. So this is aurora borealis is in the northern hemisphere, and in the southern hemisphere it's aurora australis. Look at this guy. This is Earth's aurora, Jupiter, Saturn. Why is this important?
Tell you about the magnetic fields.
So if a planet has auroras, that means it has magnetic fields. Okay? If it has magnetic fields, that implies that it has a liquid metallic core. It has you have to have a liquid metallic core, because the magnetic fields are produced by currents in the core. Okay? So that's the neat thing. This light is indicating about what is happening 10,000 miles inside the core. Okay. Yep.
Would it be possible to, like, if the metal was forming a gas? Like,
Yeah, it could. Yeah, liquid includes both liquid and a fluid is the more general term. Yeah. But but if you are in the core, you are liquid, not a gas. Yeah.
So does the size of the aurora mean anything? 'Cause
Yeah, the size would probably indicate about the strength of the magnetic field. So now if you could see auroras on planets or on other stars, I don't think we have the technology to do that yet. All right, and now I'm quickly going to go over a couple of applications, and then we'll do problems. Okay? So, let's say you take a tungsten wire. Ah. Anyway, no. Okay. All right, here's a source of electrons. A heated tungsten wire connected to cathode will spit out electrons. Now, when it's spitting out electrons of all different velocities. But for many experiments, what you need is electrons of the same velocity. Okay? So this is what is called a velocity selector, this device. It's just two parallel metal plates. Okay? And so it's a capacitor, and you connect this to a voltage source, and you create an electric field like this. Okay, so now what this is indicating is a positive charge, but it'll work for electrons is what you mostly use for. Let's say, so this is a positive charge. The electric field is exerting a force in this direction. And if you have a perpendicular magnetic field, magnetic field into the sheet of the paper, V cross B, the force is in the upward direction. So you see, if the velocity of the particle is too small, this force will be less than this guy, and two slow-moving particles will come and hit this plate. If the velocity is too large, this force will be bigger than this force, and those particles would hit that plate. Only velocities of the right particle, right speed will go through straight. So this is a velocity selector. So what this is doing is it's spitting out particles of velocity E over B. So you can, by adjusting E and B, you can choose the velocity that you want. Okay? And this is useful. All right, here's a device where it's very useful. Okay. You guys see all those numbers on the periodic table? The beryllium atom, those numbers and stuff like that? And the red numbers, the atomic weight of those guys? How did we weigh them? This is how we weighed them. This is how you weigh an atom. All right, what you do is you heat the atom, you ionize it, and then pass it through a velocity selector. So let's say you have a sodium ion. You pass it through this guy. And now you know the velocity of the sodium ion. And now you pass it through this magnetic field. And the magnetic field will bend the sodium ion, or whatever ion it is. The heavier the ion, given the magnetic field, the bigger the circle it'll go in. So this radius is related to the mass of the ion. Okay? And so the mass of the particle divided by its charge is equal to the radius. Okay, and this is called a mass spectrometer that the chemistry labs have it. Have you messed with the? Okay. So R, B naught is the field in here. B is the field of the velocity selector. This is the velocity selector. Okay, so this is a mass spectrometer. Yep.
Is this how they purify uranium for nuclear reactors as well?
No, they don't. That's they use what is it called? No, they don't do this. But this is how you weigh atoms and molecules. Yep. What is that thing called? Anyway, that word is escaping me right now. In particle physics research, so these were the first accelerators. Okay, so you had two D-shaped metal discs. You connected them to an alternating source, AC source. You put a magnetic field like that, and throw a charged particle. It would. So if you threw a negative charged particle here, when this guy is positive, it accelerates through. When it goes across that D, it's getting faster. When it's comes here, you make this positive, and it accelerates. So it's accelerating across this gap every time. And the faster it's going in a bigger and bigger circle. And so you get a particle started, it gets faster and faster. Each time it goes across the gap, it's getting faster. It's going in a bigger and bigger circle, and eventually a fast particle comes up. Okay, so this was the first accelerator. And now we have 60-kilometer behemoths in Europe. Yeah. Huh? That's the CERN. Large Hadron Collider. I think its circumference is 60 kilometers. Yeah. All right, we'll quickly mention the Hall effect. So here's, let's say you have a flat piece of wire like this, and you pass a current through this wire in that direction, in the presence of a magnetic field like that. Okay, so this is an electron going, and so the current is in this direction. So if it's a metal carrying electrons, the electron is moving in this direction, in the opposite direction. Okay. Now, when the electron is moving in this direction, V cross B would be in that direction, the force would be in that direction for a positive charge, but since it's an electron, the force on it is in that direction. And a bunch of electrons will collect over there. And this side becomes positive. And so now the electric field, so once you have enough electrons collected in this direction, they will repel any more electrons coming there. And so once that balance happens, you have a voltage develop in a direction perpendicular to the direction of the current. And this is called the Hall voltage. Okay, it turns out that if electrons are the ones carrying current, this end becomes negative and that end becomes positive. And if it's protons carrying the current, if it's positive charges carrying currents, and this happens in semiconductors, you can have holes carrying current. Okay? So let's figure this out. If positive charges were carrying, V cross B would be a force in this direction. Positive charges would collect in that direction, there. So this Hall voltage tells you what kind of carriers there are. Okay? So it's important. So again, here's a current. You pass this current in the presence of a perpendicular magnetic field, and you develop a voltage perpendicular to both these directions, and that's called a Hall voltage. So it can be used to measure the strength of this magnetic field. It can be used to measure the charge type and the carrier density. Okay, so it can do three things. All right, it's 110. I can tell you about MRIs in a second, but let's understand two things. This is a speaker. We'll see how a speaker works. Okay, what does a speaker do? I'm sorry? Yeah, so it converts an electric current it converts a current to the vibration of a diaphragm, producing sound. Okay, so now let's see how to do this. Okay, so you want to convert the electric, okay, so now let's say here's a north pole, here's a magnet, okay? What I'm going to do is I'm going to take a loop of wire and pass a current through this thing. Okay, so what is this loop of wire doing? Stick your fingers in the direction of the current. It's acting like a magnet like this. Right? All right. What is this permanent magnet doing to him? He's repelling him. Okay? Here, attach a sheet of paper to that, or a diaphragm to that. Okay, when you pass a current like this in this direction, this paper, this diaphragm got repelled in this direction. Okay? So for a current in that direction, the force on the diaphragm was in this direction. Now if you switch the current in the opposite direction, what will happen? The force will be in this direction. All right, so you took a loop of wire and you fed AC current through it, and you got the diaphragm to move up and down. There is a speaker. And if you play a good song, here's the voltage, here's the current on the good song, and that speaker played the good song. Here's a bad song, and the speaker will play the bad song too. But anyway, so you see that electromagnet is so useful. Okay, you can convert all kinds of stuff, do all kinds of stuff with it. Okay, similarly, here's a loop of wire. Remember, that's the magnet, and that turns towards the magnetic field. Okay. So in this diagram, there's the magnetic field. You pass a current, this guy lines up with that magnetic field, and now you switch the current. When you switch the current, the moment is in this direction, and again it'll turn toward that. So as long as you keep switching the current in the right at the right moment, you keep turning that coil. You turn electrical energy into mechanical energy, which is a motor. The opposite is also true. If you don't have a current, if you crank the piece of wire, you learn this in the next chapter. So now, instead of passing a current, you tie your dog to him, to the piece of wire, and have him turn the wire. That will produce a current in the wire. What is that? That's a generator. That's converting mechanical energy into electrical energy. How do you turn the wire? At a dam, you make water, flowing water, turn the wire. In a windmill, it's the wind turning the wire. Okay. So if you have electrical energy, you can convert that to mechanical energy. If you have mechanical energy, you can convert it into electrical energy using the same device. Okay. At your homes during hurricanes, you run a diesel motor whose goal is to turn that wire to produce electrical energy. Okay. All right. This is a long story, so unless you guys absolutely want to hear it, we'll stop here. This is MRI machines. All right.